Alright, time for another draftphysics.com, debatephysics.com also. Video presentation. So in the argument from series, arguments about the distinction between kinetic energy, 1/2 mv squared as the formula, and the idea of momentum as the definition of energy. And I would argue this is a hundreds of year old controversy that was never resolved with a fair fight. The truth didn't win. An evidenced argument, an argument from evidence. It was basically just propaganda, pop culture that drew a conclusion based on superficial appearances, and that was it. So there are some famous experiments. So in this argument, we're going to deal with friction. Now, there's lots of ways of explaining the concept of contact and what takes place. Now, if I was to make a video for a fifth grader, a class of fifth graders, I might try what I'm going to try to do here. This is unscripted, so it's not going to be as professional, okay? But the idea would be to explain that everything in the universe has what's called a temperature or heat. And heat could be understood as, you could say this has 75 degrees of heat, and this has 110. Okay, just making up any old numbers. And when they come in contact, they're going to share their temperature. That is, the hotter thing is going to make the colder thing warmer, and the hotter thing, by making the colder thing warmer, is itself going to neutralize its temperature. So they'll go and both end up being something like 90 degrees. And then they'll go their separate ways. Now, the idea can be understood as what temperature is just the movement of atoms inside of objects. And the idea is that they're just being pushed about. So each atom is moving a different direction. And that could be understood as being the same thing as an atom just moving back and forth, jiggling, as many physicists would say, would call it. The idea, though, is that motion could also be understood as a direction. And so when you're just taking something's temperature, you're just taking a random, what's the amount of motion in the object. And the idea would be, as if we had the right thermometer, you could also tell something's direction, the direction of its heat. So temperature or heat, you could argue, can have a direction. That is, you can have more heat in one direction than you have heat in another direction, and that would be called force. That would be called the stuff that makes something happen, makes something move. So you could say it would be the force inside of a conductor that has electricity going through it, or you could argue that it's connected to the force that pushes things around with magnets, or it's connected to the force that pushes you into the earth. All right, so the idea would be, the experiment is, so we have a classic experiment, we'll call it classic, where you could just take two objects of the same mass, and you just give one of them one velocity, and you just double the velocity of the other one. And you will observe that the one that has twice the velocity actually will travel 4 times the distance. So you give them initial temperature or energy in a direction, and you're basically just allowing contact with the ground to absorb the energy until it stops moving, until all of its differential has seeped into the ground. So the ground is you could argue, is an infinite well that will keep saying, I'm 0 temperature, and you can't make it any warmer, so every bit of your temperature will leak into the ground, essentially. And so basically you're just consuming the amount of motion or energy or heat in a direction, that an object has by having contact with the ground. And because this 2 velocity goes 4 times the distance, it does have the appearance that there's 4 times the energy. Now, it's also an appearance of 4 times the energy when you drop an object of the same mass. If you drop it 1 unit of distance, okay, it has 1 velocity. And if you drop it 4 units of distance, you only get 2 velocity. So indicating that somehow it takes 4 times the work to make something go twice as fast. When in fact the key point would be is it's only twice the time. So this falls 1 unit of time, free falls, and this free falls, even though it's going 4 units of distance, only 2 units of time. So it's only 2 units of time in contact, direct contact, where you're absorbing gravity. When you're touching the ground, you're no longer absorbing it. The ground is absorbing it, whatever you're in contact with, whatever you have friction with. So friction is just contact. It's contact on a different scale. Like in most cases, friction is used to describe circumstances where you can't see what you're moving. It's very small. But the idea is the same. So the idea is you're going to share your motion, and your motion can be understood as, the force can be understood as some element, okay? You could think of it as a little person, a little force bit, of unit of force, and all it can do is push atoms. So if you understand that the force just pushes atoms, and what you're basically just doing when you have contact with the ground is you're just taking the pushers you have and giving them to the ground. So if you had 10, you can slowly but surely give all 10 of them to the ground. You could keep 5 and give away 5. So you'd go 1/2 the velocity because you have 1/2 the rowers or pushers, or however you want to look at it. You have less force in you because you gave it to the ground. So the idea is that in this experiment you can sort of understand when you're rolling it that you know what 1 velocity looks like. This is what 1 velocity looks like. Okay, this little bit of distance, you run out of energy. And you know that has to happen when the 2 velocity rolls. There's some point where it's going 1 velocity. It's going to redo this experiment. And you know exactly what that looks like, so this is what it looks like. Just this. So you know this takes the same time as this. Okay, and it's the same distance, all right, and it's 1 velocity. It's what 1 velocity looks like. So you'd have to think that somehow here, okay, you transferred something other, and it's also just 1 unit of time. You're having contact, and the idea is that you lose half your velocity over this 3 units of distance, and then you lose the other half over this 1 unit of distance. So in 1/4 of the distance, you lose half your pushers, half the force that was the temperature, the heat that you had in a direction, you've lost. And it makes sense in the sense that it's time. How much time did you have to do that? And it's the same unit of time. So you can sort of understand as you're going slower, you're being pushed by gravity. The gravity is a time-dependent force. It's pushing you into the surface. It needs time to push you into the surface. So you have a lot more contact with the ground when you're moving slowly, and a lot less contact with the ground when you're moving quickly. So essentially, it would look something like this is how you're exchanging what you have. So the slower you go, the more exchange you make. The faster you go, the less exchanges you're making, the less friction, the less contact. So you can understand the faster you're going through a paint sprayer, the less paint would get on you. And gravity's behaving essentially the same way. It's a force pushing you into a surface. The contact with the surface is allowing your energy to be transferred to the ground. So the movement of your atoms, where you have more atoms moving, you have more stuff in you pushing this way than you have stuff pushing this way. and you're essentially going to exchange that differential with the ground and give away stuff pushing in that direction, okay, more than stuff pushing in the opposite direction, and give the energy, the heat, to the ground, the motion. Now the ground's not going to move because the ground is usually a gigantic surface, but if I made a smaller surface, you would actually see the ground accept the energy and it would start moving. If it was another object I was in contact with, the object would start moving as I made contact with it. I would absorb it, I would essentially absorb its mass, okay, and its mass would be connected to my mass, and the both would just share their velocity. Whatever amount of push there was, it would get shared. And so this gets to an experiment where you can just add mass to an object, and you start off with a one mass, and you just add mass to the object through contact, friction, and then it goes off, conserving its momentum. That is, it has the same total of mass times velocity. Not mv squared, but momentum, mv. Alright, so basically that's the argument, is that this experiment basically, even though it looks like it's demonstrating that, oh, it must be 4 times the energy because it went 4 times as far. The fact is it went 4 times as far in only twice the time, and you can understand that it was going half its speed 3/4 of the trip. After 3/4 of the trip, it's going half its speed, not halfway through the trip. So obviously something changes in terms of how it's distributing energy, and you can basically just understand, even though it looks like 4 times the work, that it did a lot less work, a lot less contact, a lot less exchanging when it was moving very fast, making poor contact with the surface, and then it did a lot more exchanging when it was going slowly and making lots of contact with the surface. So you can understand that this is really illustrating that this rolling something on a surface is still being controlled by gravity. This gravity is the pushing force, and that the pushing force can't push you any but more than the same amount per unit of time. And just like a paint sprayer, it's only going to throw so much, and if you go quickly through it, it's not going to push you very hard. So this also goes to arguments about thin ice and the fact that you can get away with crossing thin ice if you can get yourself up to a high enough velocity, okay, to basically escape the time gravity needs to impose pressure. So gravity needs time to push you into the surface, to make contact with the surface. And if you go quickly across the thin ice, you obviously won't make much contact because you won't be absorbing much gravitational pressure, and therefore you won't weigh per foot the same amount, and therefore you'll put less pressure on the ice and not break the ice. But if you go slowly, gravity will give you velocity, it'll give you momentum into the ice, contact, and you will exchange, and the atoms of the ice will feel the pressure and will yield to it. All right, so that's how I would explain it. Force is, the ancients weren't entirely wrong in a lot of what they deduced based on really crude, a very dim picture of the world. They didn't have a good microscope. They had a cheap magnifying lens, and but they did a lot of good reasoning. And the idea that there's this hard and useful appearance, that it does move, force moves like a liquid, like a substance, like a commodity, that one thing has it, When it gives it away, it doesn't have it anymore. And there's only a certain amount of it. So people like Descartes, back in the 1600s, made these kinds of arguments that the universe basically has its energy already in it. The energy, the pushers, just move from an object to an object, and they can push like a school of fish, where the school of fish can have fish moving in all directions and therefore go no direction, or all the fish can move in the same direction and the whole school move. And that the idea is that this energy can do the same thing, that it can be in something that doesn't appear to have any energy because it's not moving, or it can be easily converted into stuff moving the same direction, and revealing the fact that it has this heat in a direction. But it's all conserved. So there's only so many things that can push in the universe. There's only so much to be pushed. And all that really happens is, in every action that takes place, is you just transfer pushing bits from one object or one substance to another, from one atom to another. You give this force, and the force moves the electrons and protons first, then the atoms, and then the molecules, and then the compounds, and then the bigger objects. And it's all by transferring this stuff moving at the speed of light, these pushers, that are pushing the matter. And all that really matters is how much mass there is and how many pushers, and that'll tell you, that's all you need to know. So if you see a piece of matter and you know how many bits of energy are inside of it, and that you know that there's a differential in direction, that is, you don't know the absolute number, but you know that there's 10 more going this way than it's going that way, then you can say it has a velocity in this direction because it has a disproportion in that direction. And that's all you're really seeking to see, is the disproportions, the differences in how much total energy versus energy in a direction. But the energy in a direction is always related to how much mass is it and how many pushers do you have more going one way than another way. And you just figure out how much mass there is and how many pushers there are, how much force there is, and that's all you have as energy that can be exchanged. All right, so that's probably enough. I don't want to make these videos too long, but it's a very good argument against kinetic energy, in that it all fits together, that you can understand that the energy has to be conserved, that the energy is just in a form of something that moves an atom, that the atom can jiggle in all kinds of directions, or it can go in one direction. You can have liabilities, deficits, IOUs. You can have debt, and then you can have something where you're gaining profit, you're collecting rent. So you have assets and you have deficits, and all that's really taking place is you're just exchanging your currency with everything else you have contact with. When two things bang into each other, they start to share their condition. If this one has 7 extra going this way and this one has 7 extra going that way, they're going to try to share that condition. And if they're elastic, well, then they're just going to basically, you take my $7, I'll take your $7, and now we'll both leave with $7. And any other circumstance, it's going to be the same circumstance. The total amount of currency, the total amount of motion always has to be conserved. So if 14 goes in, 14 has to come out. You can never kill the force or destroy the pushers. Yeah, so we'll call that enough of a video. And so that's the second argument from contact or friction, or the nature of force and motion, the nature of contact and exchange. That's what runs the universe, is exchanges. And something real is exchanged, something finite is exchanged. There is no make more by just banging things into each other, making more, pushing energy, or pulling more energy out of it when it doesn't have it. More difference or differential. Heat in a direction, okay, like heat, just has to be conserved. All right. Yeah, good enough.